So here are the questions we're working on today. We're at the week 10 finally. We're almost done. We've only got a couple more things to cover in class, but we still have a lot of things to cover in class. Today we're going to be working on 9.2, just number 12. We did some other ones last time. And then we're going to move on to some of this 10.1 material. So what do we got for 9.2 number 12? I know it's a graph one.
It gives you a graph of natural log of A versus time. And the equation for the graph is y equals negative 0.05x.
Wait, sorry, 0.05x.
Plus 1.6094.
Okay.
And then it just asks what the reaction order is, what the initial concentration of A is, and what's the half-life.
Okay, so 3 things to answer. We can get a lot of this by understanding how this equation relates to this graph relates to the integrated rate laws. So we can write down the integrated rate law underneath this, which is going to be natural log of A. We can tell because that's our y value, is equal to negative kt plus natural log of A0. So right away we can tell, we can figure out the initial concentration. First off, the order is 1, because it's a natural log A plot is linear. We can figure out the initial concentration from this. We can just do e to the 1.6094 should be equal to A naught.
Yeah, give me a second.
Oh, it doesn't matter which way the plot's going. And then I can tell, since my x is t, I can tell this is my k value.
It's really 5.
And I can do t1 half is equal to natural log of 2 over k.
We got a solid 4.9998. So 5.
4.999.
9. 5. 999. There's more 9s. Never enough 9s. There you go.
Right? So by understanding how the equation they gave us relates to the integrated rate law, recognizing its first order, it just becomes a matter of recognizing how the slope gives us a negative k. Notice this is negative k, not k. So our t... Wait, was this a negative slope?
Yes, it's negative 0.05.
Okay, I was about to freak out. Okay. Because we can't have a negative t1 half. And so I was about to have a little panic attack that I did something terribly wrong. There we go. So our k is just 0.05. Natural log of 2 divided by 0.05 gets us our t1 half. Right now, this is, again, the integrated rate law. The usefulness of the integrated rate law is it gives us this way to characterize how fast a reaction is happening while the concentration is actively changing. The original rate of reaction was not a great way to do this because as the reaction proceeded, the rate was changing. So if the rate is changing as the reaction is proceeding, then it's not going to work. So we had to go to integrated rate laws in order to look at how the reaction proceeded as the concentration was changing, which is going to change the rate as it's going. We came up with 3 different ways to relate it: 0th order, 1st order, 2nd order.
So if we were graphing this instead of against the natural log of the concentration of A, and instead of just straight concentration of A, and it was still a straight line, then it would mean it's a 0th order?
Mm-hmm.
But since how could we tell if it was 0th order if we're graphing it against the natural log of A? Can we tell or no?
It wouldn't be a straight line. So if we
curve,
it'd be,
up,
I think it'd be curved concave up. It would just be a weird curve, right? And we're going to see this in lab tonight. So we're going to do a lab where we actually determine the order by using integrated rate law for the blue dye bleach reaction we did on is today Tuesday? We did on Thursday,
Unfortunately.
because it feels like Friday. Because on Thursday, a lot of you from that first kinetics lab got the wrong answer. You did all of your data analysis correctly, you collected data, but it looks like the data you're using is just not that great.
Thanks.
Okay. Well, I mean, first time trying to collect rate type data, it makes sense that it didn't go perfect. So that's number 12. Let's go ahead and move on to 10.1 and see what we got going on in 10.1. Other questions about this before I erase?
I had a really quick, just Eunice question.
Sure.
Um,
About this or something else?
No, it's not.
Let me erase while you're asking.
Okay. So, like, if you're finding E cell standard from delta, and you have delta G, right? So you have like a delta G standard. So you have delta G standard equals negative NF E cell standard.
Mm-hmm.
And then so you're solving for E cell standard. So like I can't get all my units. I can't like I have joules and coulombs, so I can get like volts, but I don't know how to get rid of the mole from the delta G where it's like joules over mole. So I'm not sure.
Faraday's constant. Let me look at how it's given on the equation sheet. Faraday's constant is 96485 coulombs per 1 mole of electrons.
So doesn't that get rid of
Your N value, how many electrons did you have transferring?
2? Oh, is
That's
that just
2?
2 electrons, not 2 moles of electrons? Oh no, it is. Okay.
2 moles of electrons per 1 reaction.
Oh.
Right, your delta G
Oh, I see. Okay.
is going to be in kilojoules per 1 mole reaction. And this is kind of the subtlety of like, when we write down N, we just say it's 2 moles of electrons transferred.
Mm-hmm.
In our head someplace, we should say 2 moles of electrons transferred per mole of reaction.
Right.
The delta G is given in kilojoules per mole. It doesn't specify the moles. Like, you can tell from the context it's moles of reaction.
Yeah.
But can you really? Right? I like to write those things out explicitly, especially when we are doing our unit analysis. Okay, 10.1, here we go, last homework assignments. What does 10.1 number 2 ask us to do?
Ingredient freezes at, well, I mean, no, it's from units. Do you want my units? Or
You asked, let's get your units.
Okay. So Incredium freezes at negative 130 degrees Celsius and boils at negative 57 degrees Celsius. The enthalpy of fusion is 6.24 kilojoules per mole, and the enthalpy of vaporization is 43.2 kilojoules per mole.
Hang on a second. The delta H of vaporization was?
43.2 kilojoules per mole. Calculate the change in entropy of the incredium when 6 moles melt at the normal temperature.
Okay, so all of this information is given because there's like 3 different ways that I might give you the problem.
Mm-hmm.
I might ask you about the entropy as it melts. I might ask you about the entropy as it boils. I might ask you about the enthalpy change over a certain range. There's a couple different ways that you get the question randomized. Yours was specifically asking...
calculate the change in entropy of the incredium when 6 moles melt at the normal temperature.
Okay, so this is a review problem from back when we first learned about entropy.
Yeah.
And we said there were, entropy in and of itself was this relatively strange way to think about, energy dissipation, where energy density was and how energy moved. And it became important as we started thinking about delta H because there was this cost in keeping energy densely packed together or energy spreading out. There was a cost we had to deal with. And we said one of the only places where we can really get a specific calculated number for entropy without looking at our other tables was phase changes. And that was specifically when we were looking at, so this was melting we're looking at? Melting,
Yeah.
I have it written down. So this would be the delta H of fusion over temperature
Yeah.
times some number of moles.
Yeah.
That should be it.
That's what I did, but then I think, like,
Now we're melting, so that should be an increase in entropy.
Yeah.
Right, so yeah, we're gonna use the positive version of that.
but the only thing, yeah, okay, let me try it again and then.
Keeping in mind, delta S should end up in joules,
Oh, okay, that's why.
moles.
Yeah, it's
Kelvin.
It's just because I didn't do Kelvin. Yeah, that's why.
Oh, you gotta do Kelvin. You're gonna divide by negative temperature?
Yeah, that's what I did, and I was like, why is, like, okay.
Right, so dividing by a negative temperature is gonna get you a negative entropy change, which should not make sense. Logically.
It's plus 273.
Plus 273.
Okay. Okay.
Okay, so unit analysis again. That's number 2. Any questions on number 2 before we move on?
So for this, since it's melting from like ice to water, we're taking it from the freezing temperature?
It's only, so the phase change happens at the freezing temperature.
Yeah.
Right, so that would be the negative 130 plus 273 is going to get you to 140-ish. 140 Kelvin.
143, yeah.
Yeah, there we go. Okay.
Okay, so the third question is, we mix 22 milliliters of 10 molarity HCl aqueous with 19 milliliters of 10 molarity KOH aqueous.
Jeez Louise.
If both solutions are initially 85 degrees Celsius, how much water boils away? And then it gives you the reaction, which is HCl aqueous plus KOH aqueous goes to H2O liquid plus KCl aqueous, and the delta RH standard is negative 57.3 kilojoules per mole.
Okay. So, they're both, so this is absurd on a couple levels. One, why would you have high concentration acid and base up at 85 degrees Celsius? Wild. But essentially what we're looking at here, there's a couple hints in terms of what we're thinking about is a how much boils question. We've got a temperature, we've got a reaction, we've got a delta H. What are we going to do?
Calculate the Q.
Yeah. What are the equations we're going to use to calculate the Q?
Like N times delta H. Q equals N times delta H. Oh wait, because it's water, so we also use MC delta T because you get to 100 degrees.
One other thing.
And delta H.
Hey, let's go.
Right.
Oh, and delta H.
The vaporization. Now, out of this, which thing is going to be the unknown variable based on the way the question was asked?
I think the vaporization.
Which part of the vaporization?
The delta H of vaporization.
No, we got that on the
N.
table. The N, right? How much? That's going to be our question. So we can look at the N delta H of reaction, the MC delta T, and the N delta H of vaporization, where this is going to be our out, and these two together are going to be our in. Right? And I like to make my out the exothermic thing, so the chemical reaction. I can, because it's a 1-to-1 mole ratio, I can already tell potassium hydroxide is my limiting reactant, and I'm going to have 0.019 times 10 moles per liter. Going to get me 0.19 moles of reaction. Right, so there's some stoichiometry we have to do in there. The stoichiometry was not really the point of this problem, so the stoichiometry was relatively straightforward. 1-to-1 mole ratio with one thing obviously being the limiting reactant, the smaller number. Right. So that means I can go ahead and I can start plugging things in to figure out what's going on. I'm going to have negative 0.19 times negative 57.3, right? That negative is because it's negative Q out is equal to Q in. So I got my double negative there. I'm going to go ahead and multiply this into joules while I'm at it, so my units match. That's going to be equal to MC delta T. That's going to be those two numbers added together. That's going to be 41 times 4.184 times 100 minus 85. It's okay to leave it in Celsius. This is the only time it's okay to leave it in Celsius because it's a delta T. The plus 273 minus 273 would cancel out. So that will get me how much energy to bring it to the boiling point. And I'm going to have plus N times the delta H of vaporization, which I can get off the equation sheet, as 40700. And again, I converted it to joules. See you later. See you tonight. And now you'll notice the only variable that I don't have written in is that N for the number of moles of water that will boil. A couple things to look out for. If I get an N that is negative, I've done something wrong.
And we just use the N for the limiting reactant for this?
Well, no, we figured out the limiting reactant. So these are two different N's, right? This is the N of reaction versus the N of water boiled. Right? This is an N reaction, this is N of boiling. So this is moles of reaction that happened, this is moles of water that boiled. They're
Okay.
two different N's. One of them we know from the information that was given because it told us how many moles of, it told us the volume and molarity of acid and the volume of molarity of base.
Yeah.
So I can figure out the moles of reaction by looking at how many moles of acid there are, how many moles of base there are, figuring out which one is the limiting reactant. And that limiting reactant is going to be the moles of reaction. Relatively straightforward because everything is 1-to-1 mole ratio, so it's just smallest number.
Okay.
If it was a 2-to-1 ratio, we'd have to be a little bit more careful to make sure we get the proper limiting reactant and then get that converted to moles of reaction properly.
Since you have we have the delta H of reaction, could we just do, like, once you put the, like, you put it into moles, you just multiply it by that for both of them, and then whichever one the lesser one is, that's the limiting reactant, or is that not right?
That would also work.
Because then you just don't have to do it again, I guess. I don't know.
But I can already tell.
Yeah, but I meant for like a...
For a more complicated situation, yeah, you could do it through moles of reactant times delta H to figure out which one is smaller. It's the same as doing moles of reactant to figure out which one has less moles of product.
Wait, so wouldn't the 41 that we have right there be the N that we're looking for in the problem? I'm confused.
No, the 41 is the total amount of water. That's not what the problem is asking for.
It's looking for the moles of water.
Specifically, keep reading.
Water boiled.
Moles of water boiled. It might be 0 moles of water boiled. This reaction is exothermic, it's giving off a certain amount of heat. What if it only raises the temperature from 85 to 95? Then you boil no water. That's a possibility. The 41 grams of water you have gets up to 95 degrees Celsius, or maybe it gets up to 99 degrees Celsius, but it's not boiling. So maybe it's 0 moles boiled. If it hits 100 degrees Celsius and then keeps putting energy in, that extra energy that goes in will go into boiling.
Oh. Here I only see that if we have it equal to the MC delta T, what happened to the N delta H and then the delta H of the vaporization?
That's this.
Oh, okay.
That's the N delta H of vaporization plus the MC delta T. That's on one side of the
Okay.
equal sign.
I didn't. Alright. It was just like down there. Never mind. And then like the 0.19 is the moles of whatever that is, the KOH or whichever is the limiting reactant. right? And then from there we take times the delta H of reaction, which we have at right there, and then set equal to the grams, which is really just the milliliters of water, which we get from the product side, right there.
Mhm. No, we don't have to do product side to get the milliliters of water, right? We get the milliliters of water from total volume of solutions added together.
And milliliter goes directly to grams.
Yep, because it's water.
Wait, so then it just we just add all of it together.
It's just 22 plus 19. That's how I got the 41.
Well, then what about the KCl? I don't know. Is negligible?
Negligible. Also, the H2O produced, all of that stuff is in the total volume of the original solutions, right? So those things, as the reaction proceeds, the total volume should not be changing.
Huh.
And the Ks, the Cls, all of that stuff is technically at concentrations this high. Now this is where it gets curious, right? At concentrations this high, approximating this to just be water might be incorrect. That is to say, I think this would have a higher density than H2O. I think it would be like 1.1, not 1.0, right? I think the density of water, so the grams of solution, I think with that much molarity, I think the grams of solution would be off. Also, the heat capacity with that high of a concentration, I think the heat capacity would be a little bit higher. I think the heat capacity would be changed. But we're approximating it. Usually when we did this, we've always approximated water solutions to be pretty much just water. And that is close enough, right? So we could ignore the KCl, the salt that's being produced. In this situation, with concentrations this high, we're still doing that approximation, but I think the approximation is less good. Because concentrations that high, a significant amount of that solution is going to be KCl. That's going to change the, also, if you have salt in solution, does that change the boiling point?
I feel like it would.
It does. So we could look at this and say, after the reaction happens, how many ions are in solution? How does that change our boiling point? Well, that'd be such a good question.
You use
That'd
like
be
an
so-
ice table?
No, that would be colligative properties. So you just do straight stoichiometry. You'd have to calculate the number of ions in solution. Use that number of ions in solution to calculate a molality. Use the molality to get delta T of boiling point to see how the boiling point of water changes. That'd be a cool problem.
Dude.
Can we do
I mean, I would have to design it very carefully. We could see. Let's see.
that? I kind of
I-
realized I low-key forgot how to.
I would have
how to
no
do
chance
that.
of that. Yeah.
Um,
if you ask me to do that right now, go
Molality?
yeah,
Double
sorry.
check.
Unfortunately,
let's
will not be available.
let's go ahead and see what we can figure out. Are we good on this part of it? We got our
Yeah.
N value. We got like 3.676 grams boiled.
Yep.
Does it ask for grams or moles?
Grams.
Cool. So it's like 3.67 grams. Okay. For fun, let's go ahead and change this to problem 3 bonus. We're going to do something, the problem does not ask us to do this, but we're going to do it anyway. What would be the boiling point? Okay. So what we have to consider is we've got I've got 0.22 moles of HCl and 0.19 moles of KOH. This is going to be a pretty big headache because normally when we've done this, we've only done it for one component in solution. So what we're going to do is we're going to get the how would we do this? We're going to essentially say, look, the amount of excess H plus is not going to matter. We're really just going to focus on the moles of KCl as the thing that's going to change our boiling point. Technically, the H pluses in solution might also change the boiling point, but we're going to just look at the KCl. So we're going to say how much KCl is there, and it's going to be 0.19 moles. Technically, there's a leftover 0.03 moles of Cl minus and 0.03 moles of H plus that we're not dealing with, but I'm not going to worry about that right now. Let's just say how much this 0.19 moles of KCl changes the boiling point. Now, to get to molality, molality is moles of solute over kilograms of solvent. So we're going to have 0.19 divided by, we had 41 grams, that's going to be 0.041 kilograms. And that's going to get us our molality, 0.19. Our, ooh, jeez. Our molality is 4.63. This is where I'm like, this high of a concentration is pretty wild. 4.63 moles per kilogram. Now, my delta TB is going to be IKF molality. Where if I'm just looking at the KCl, that's going to be an I of 2. Freezing point constant for water is 1.86, and my molality is 4.63. Oh my god. This is wild. So I've got this 10 molarity solution, 2 times 1.86 times 4.63. Sorry, 17.2. With that much salt in the solution, it's not going to boil until we hit 117 degrees Celsius. It doesn't boil at 100 degrees Celsius. So this problem of like pretend like it's just water actually doesn't work in this case because of those high concentrations. Those high concentrations totally throw off our approximation of it's just water.
Wait, why'd you add 100?
Because this is the delta TB, right? So we're going to increase the regular boiling point by 17 degrees.
Okay.
The regular boiling point is 100 degrees. It becomes 17.2 degrees higher. The boiling point becomes 117. So I don't think, with that in mind, we would boil, we just calculated 3.6 grams of water would boil at 100 degrees Celsius. It ain't going to boil at 100 degrees Celsius with that much salt in solution.
Yeah.
Right? That approximation that we make in the problem is actually incorrect. Isn't that neat?
Yeah.
Now, we didn't run into this problem previously because we always used much lower concentrations than this for our problems. We were using like 0.1 molarity. And in those situations, we'll see the boiling point change by like maybe like half a degree. Technically still is changing, still throwing off our approximation, but not enough for us to really concern ourselves. In this situation, the boiling point is changing pretty significantly. And that's without taking into account the extra moles of HCl that's left over, which is also going to have an entropic effect. That's just with the KCl that's being produced, those ions in solution. Pretty wild.
Yeah.
But good reminder of how we think about boiling point change.
Yeah.
Okay.
But what was the I value actually?
The I value is the Van Hoff factor. A lot of people had trouble with that in class as well.
Is that just like a?
It's just like what the ion number.
So it is. Remember that boiling point change is a completely entropic effect, and so this is like an entropy scaling factor, right? If we just put KCl as one thing in there, that's just one thing going into solution. And so that would have like one effect. But if we recognize that KCl breaks apart into 2 ions, that would be like putting twice as much stuff in there.
So it's like I just like a constant that we multiply by.
Yeah. And it's just, the constant is the number of things being put into solution. 1, 2, 3, 4, 5, 6.
And then the KF is
Boiling point. Oh, sorry, did I write KF? That should be KB. My apologies. Let me make sure I looked up the right value. I knew it was supposed to be KB. Oh, I totally messed up. Hold on. I looked up KF instead of KB. That's the freezing point constant. It's not going to be as dramatic as I thought. Oh my goodness, embarrassing. This is what I get for going too fast. Let's try that again. 2 times 0.512 times 4.63. No, okay, that's 4.74. 1047. 104.74 degrees Celsius. Okay, that's way less absurd. Thank you for catching that. I had a typo. It's supposed to be KB because we're looking at the boiling point change. The boiling point change constant is different than the freezing point change constant. So we got to take that into account. Can't interchange those things. So the error is not nearly as dramatic as I thought, right? It's just 104 degrees, but that's still 4 degrees hotter, which means 3.6 grams is still not the right amount that would boil. It would be less than 3.6 grams. Yeah, but definitely pay attention to those subscripts. Make sure you get them right. That was number 3.
Oh, I mean, kind of.
Number 3 plus the bonus. Ready to go on to number 5?
Yes. Okay. Bold already.
Number 5 is.
Hold on just a second. Man, I think I'm getting sick.
You think?
You got me. Students got me.
I'm innocent, dude. I've done nothing.
Not you two.
I don't know. I chugged that emergency, you know.
Okay, number 5. What do we got for number 5?
Okay. So a sealed 3.5 liter container initially holds 0.0132 moles of hydrogen gas and then 0.084 moles of solid iodine. And then 0.0638 moles of hydrogen iodide gas. So when equilibrium is reached, the concentration of hydrogen is 0.00658.
The concentration?
Yeah.
Is
0.0065 molarity. And then calculate the value of the equilibrium constant for the reaction for H2 gas going to I2 solid.
Going to I2 plus I2?
Plus I2 solid going to 2HI gas. And then for the equilibrium constant, use a 1 molarity standard state, not a 1 ATM standard state.
Atmosphere.
Okay, yeah, because we're not doing it in pressures, we're just doing it as concentrations. Okay. So, we know that at equilibrium, this is going to be the concentration of HI squared over H2.
Mm-hmm.
Does the I2 matter?
No, because
It's a solid, so it's not going to be active in the reaction equilibrium.
Yeah.
Still matters that we have enough of it, but so we need to get these values at equilibrium. I know my initials, right? These are the initials. My initial concentrations. And I give these in moles instead of concentrations?
Yeah.
Silly. Right, so we have to, it just puts an extra step on us, right? 0.0132 divided by 3.5, 0.084 divided by 3.5, and 0.0638 divided by 3.5. We have to get those, if we want to get our initials, we got to get them into concentrations. So we go ahead and we convert all of those to concentrations. 0.0132 divided by 3.5 gets us 3.77 times 10 to the minus 3. 0.084 divided by 3.5 gets us 2.4 times 10 to the minus 2. 0.0638 divided by 3.5 gets us 1.82 times 10 to the minus 2. So, oh, this is funny. Notice my initial concentration, if this is 6.5 times 10 to the minus 3, my equilibrium concentration of H2 has actually gone up.
Yeah.
So that means during my change step, I'm going to have a plus x minus 2x. And I can figure out how much it must go. I can figure out this x is because I know at equilibrium, this is 6.5 times 10 to the minus 3, which means I can figure out just from this chunk, I can figure out, right, 3.77, or 6.5 times 10 to the minus 3, 6.5 times 10 to the minus 3, minus 3.77 times 10 to the minus 3, 2.73 times 10 to the minus 3. And then I can use that x to calculate these two things. Right, so I can do 2.73 times 10 to the minus 3 plus 2.44 times 10 to the minus 2. It's going to get me 2.713 times 10 to the minus 2. And then I can do 1.82 times 10 to the minus 2 minus 2.7 times 10 to the minus, sorry, 2.73 times 10 to the minus 3 times 2 negative is equal to that.
Wait, are you sure that's right?
What?
The second one?
Pretty sure. Wait, did I add or subtract? I added.
Wait, maybe I did it wrong.
Right, 2.73 plus 2.4, unless I rounded too much, but I think that's right.
I'm getting 0.02673.
Plus 2.73 times 10 to the minus 3. Oh yeah. I messed up someplace. Thank you. 2.673 times 10 to the minus 2. And then we'll do 2.73 times 10 to the minus 2 times 2 plus 1.82 times 10 to the minus 2. Oh, wait, I messed up.
I got 0.01274.
3, 2. I'm right behind you, plus 1.82 times 1.274? 0.01274?
Yeah.
1.274 times 10 to the minus 2. Right, and we kind of did something that doesn't really matter, right? This I2, not relevant, right? It's solid. Does not participate. So then I can just take my HI concentration. I can say KEQ is equal to 1.274 times 10 to the minus 2 quantity squared divided by 6.5 times 10 to the minus 3. And I can get an equilibrium value for that. Ooh.
I think it was just like the units that like confused me when I was doing it at first.
Yeah, so the fact, that's kind of irritating, that they gave it to you in stoichiometric values of moles and then ask you to do an equilibrium calculation of concentrations. Kind of weird. Yeah. It makes me think that this problem originally had something where you had to do a stoichiometric calculation before you did your equilibrium. And then at some point, either I or somebody else was like, this problem's too complicated, and we got rid of the
first part.
the stoichiometry part, but left it in stoichiometric values. But then we can plug that in. 1.274 times 10 minus 2 squared. Oops. 1.274 times 10 minus 2 squared divided by 6.53 times 10 to the minus 3. 2.48 times 10 to the minus 2.
Yeah.
Cool. Notice this equilibrium constant is reactant favored. And because we started with some product already there, we had the reaction go backwards in order to get to equilibrium.
I was wondering if we could do maybe like the first part of question 8, because
Did you want to see question 7? Or
I do, but there's only 8 minutes left.
oh, let's do the first part of question 8 then.
Because question 7, I think it's like something you've done in other office hours, so I can go back and watch it probably.
Let's look at the first part of number 8 real quick. Questions about this before we go on?
No, I think
Okay. Let's look at number 8.
Wait, so what's that exactly, like that kind of problem called though? Like, it's
The one we
actually-
just did?
Yeah, that's what that
It's
was.
just an equilibrium problem.
Okay.
Now, I say equilibrium problem, but there's like 10 or 15 different types of equilibrium problems, right?
Yeah.
This was an equilibrium problem given equilibrium values or a way to find equilibrium values, calculate your KEQ. It's the opposite of what we've usually done, where usually we have the equilibrium constant and you're asked to find the equilibrium values. This was, given the equilibrium values, find the equilibrium constant. It's a little bit backwards from what we usually did. Okay, what's number 8 have us do?
Alright, so it's an E-cell question,
Okay.
or a cell potential question. So the cell is Ag solid, Ag iodine solid, and then
Is that the reactants?
that's the reactants, yeah. Or the anode.
Oh,
Same.
that's the anode?
Yeah, it's the anode, and then
Okay.
the cathode is copper 2 plus aqueous plus copper solid, or not plus, sorry, and copper solid, and then the temperature is 298 Kelvin. And then they give you the balanced reaction, I think. 2 Ag solid plus 2 iodine minus aqueous plus copper 2 plus aqueous goes to copper solid plus 2 Ag iodine solid. And the delta G standard of reaction is negative 94.6 kilojoules per mole.
Okay.
And then, I don't know how, but I got my E-cell standard wrong and I can't figure out why it's
How
wrong.
did you calculate E-cell
So I
standard?
did delta G standard is equal to negative NF E-cell standard. And then I solved for E-cell standard, so E-cell standard is equal to delta G divided by negative NF.
What'd you do for N?
I did 2.
That seems right to me.
Yes, I don't know what's wrong. I'm really confused. Maybe let me try putting my calculator again, but like I don't
Yeah, let's
think.
double check it real quick. That seems right to me. You've got the delta G. We got 94.6 negative divided by 2 divided by 9,645 negative. You got 0.49?
Yeah. And then,
What
so I put that
formula?
in, and then I usually put in like another number, like
Mhm.
fake number, and it said this is not correct. But I was like, maybe it's just for both of them. And then
It might be checking for both of them. Let me check something real
But
quick.
then I
So
did the E-cell
I believe
value.
that's how you started. So
But then I did the E-cell value.